Hello everyone, I'm Feng. I'm going to present our work on attentional separation and aggregation network for self-supervised depth post-learning in dynamic scenes. Molecular depth estimation is a task to recover the depth map from a single image. For visual geometry, we want to estimate the motion of camera between two frames, and then we can get the full trajectory. They play important roles in 3D vision applications, especially for robotics, autonomous driving, and AR. In 2017, Joe proposed that we can jointly train these two estimators, getting rid of the requirements of ground truth data from expensive sensors. This joint learning framework uses the knowledge of structure from motion, and uses the epipolar geometry to warp one view into another using the estimated depth at pose. Then the pixel-wise difference between synthesized image and the original image can be the training signal. The photometric error is like this. Large errors occur at the region of this moving car. It's a great challenge for this method and its variants. It's because that in this manner, we compute the rigid transformation using the ego motion for each point in the view. But it's invalid for the moving objects, leading to unexpected errors. It's bad for our training. Therefore, we need to compute the dynamic transformation for the moving objects. Some prior works also notice this issue, but there is not a method that can handle objects moving at arbitrary speeds without exterior pre-trained models. Motivated by Gordon, we can estimate the dynamic motion field from two consecutive frames. We design a new ASANet to replace the original encoder or postnet, which can separate and extract static and dynamic features from adjacent frames. Besides, we extend the commonly used postnet to MotionNet, which incorporates an additional motion field decoder. In order to achieve dynamic transformation, we further propose an auto-selecting mechanism. First, let me simply introduce our ASANet. It's a variant of ResNet with a novel ASA block. There are two ways sharing feature propagation passes inside the model. In each layer of each pass, we first compute an attention mask, and then use it to decompose features into static and dynamic parts. Finally, the decomposed static and dynamic features from two passes are aggregated into a new pair of features and fed into the subsequent layers. For effective training, we train our method in a three-phase schedule. In the first phase, we train the depth estimator and ego motion estimator with some popular loss functions. Then we freeze the depth net and ASANet to optimize the motion field decoder. Similar loss functions are utilized, but we use the estimated motion field to compute the dynamic transformation for each pixel in to handle moving objects. In the last phase, we jointly train all components in our system. We merge the two optimization passes through the auto-selecting mechanism. The ASM can generate a dynamic mask. It can decide that which points are better with the dynamic transformation. Here are some results on KITTI benchmark. For depth estimation, we compare our method with the existing methods, and the results show that our method can achieve state-of-the-art performance. And despite a performance gain, we use the standard U-shaped depth net without any additional computation cost. For visual geometry tasks, our method can achieve the best in one-stage end-to-end view methods, and maintain a real-time operating speed of 50 fps. To visualizing the effect of our auto-selecting mechanism, we present two videos here. It demonstrates that our method can automatically detect the moving objects and compute their transformation to decrease their photometric error. There are still some shortcomings for our method. First, some moving objects will be missed or incomplete in some frames. Second, there are many noises in the dynamic mask in addition to moving objects. We will try to solve these problems in our future work. Thanks for your attention.